Hey, this is Physics 2211 Lab 3 of the Black Hole by Karthik Chilkapati. So, our introduction, the purpose of this lab is for us to use computational models to find the mass of the black hole, which is done in part 1, and to find the trajectory of a planet and starship around the black hole, which is in part 2. For our fundamental physics principles, we are going to use are going to be our F force in gravity, which is negative g m1 m2 over r squared times the direction r vector. And we have momentum equals mass times velocity, and force net equals the rate of change of momentum. And looking ahead, our results for part 1, the mass of the black hole turned out to be 9.6 times 10 to the 33 kilograms. And our velocity of the ship that we had to put as our initial was around negative 6 times 10 to the 6 in the x direction, 8 times 10 to the 6 in the y direction, and 0 in the z direction meters per second. So initial conditions of the lab, on the left we have for our code for part 1, we had to have a gravitational constant. We chose the mass of a star. I just chose around like the same mass as the sun because that's just a general reference I took. And then this is our delta t, which was calculated by multiplying time times day per year for like an orbit. And then over here we have it for part 2. Here we can our initial conditions. We're gonna have our mass from part 1. These were all given to us, but they are going to be our mass of the planet given, our gravitational constant, mass of the ship, delta t, and our initial time. And here are the initial velocities that we had to find at the end. So for part 1, our system is the star and the black hole, and our surroundings are space. We basically had to use velocity and then calculate our momentums with each of these initial and final velocities to basically find our delta p for our change in momentum. And when we divide that by time, we get our dp dt, which is basically what f net equals. And with that, we were able to find the mass of the black hole at the very bottom, because if we know what f net is, we can rearrange our original force gravity equation to find the mass of the black hole. And once we did this calculation, we got our mass of the black hole to be 9.6 times 10 to the 33 kilograms. For part 2, we had to find the trajectory of a spaceship going around the black hole, as well as uh, with another planet also orbiting the black hole. So here our system is a black hole, the planet, and the starship, and their surroundings are space. Basically, we had to do basically this second snippet of finding the net forces on each of our 3 objects in our system. So, for example, this is the one we did for the planet. We had to find our force on the planet by the black hole and on the planet by the ship, and we added them all together. And we repeated the same thing for the black hole and the starship. And then to find the position and velocity of our planet and ship, we basically used Newton's second law to find these values by this equation right here. So playing around with the velocities in the x and y direction, I found that these 2 values were probably the best values that I could find, so that the starship wouldn't crash into the planet nor get sucked into the black hole. And there are sources for error in this because we don't know exactly what would be the best exact velocity in x and y direction, but as I played around with it, these are ones that I found that work. So going on to our what if and what does it mean questions. So our what if is discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So as we saw in our code, we did see that we set our F net equal to dp dt. So we do know that those 2 values are equal, and so must their components be. But for calculating each of these individually on their own, we use a different method. So for FNet, basically, we will have to know all of the forces acting on the system, which is why I said that we had to find everything acting on the starship, everything acting on the planet, and everything acting on the black hole. And then with this, we can, once we know all this information, their masses and their distances from each other, we are able to find FNet. But for finding the rate of change of momentum, we only need the mass and the velocity of that single object. And then what initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? This was kind of hard. I couldn't find the exact numbers that would need it for this, but using logic, I was thinking that the perpendicular component would need to be not too strong from the black hole to where like the ship would have to be dragged into the black hole. But then again, this it can't be the same as a planet because that would basically go in the planet's path of trajectory, causing them to crash. And that is all I have. Thank you.